So we're going to take a second and talk about RL circuits here. R referring to resistance, which is a constant value of ohms, and then L being self-inductance measured in henries. And so you see R and L in this diagram, which is figure 9.9. I've grabbed these words from our text in the picture. And so what we're looking at here is we're dealing with a picture where we can close A and B to connect a constant electrical source of V in volts. Right? We already know Ohm's law, or you may know it from one of your physics classes, but voltage equals the resistance times the current, I. And then for this type of circuit, we augment it and we use this form here. So L, our self-inductance, times the rate of change for the current, plus the resistance times the current would be equal to the voltage. And as a note, current is measured in amps, time is measured in seconds. So we're going to do an example here. We're going to be dealing with the switch in an RL current. And suppose that it's closed right at time equals 0. How will the current flow as a function of time? So we're going to start with that differential equation given up there and put it in standard form. So we're starting with L di dt plus Ri equals V. So in this format, we've got to rearrange it so that it's in standard form. So I'll divide everything by L. I'm dividing by L, I've got di dt plus R over L I equals V over L. All right, so we're dealing with an equation that is I in terms of t, right? So instead of y in terms of x, here we have I in terms of t. And if we want to identify what our p function is, P of t is R over L, and Q of t is V over L. So if we want to find our integrating factor, V of x, remember that is e to the integral of P of t dt. Of course, I wrote V of x there because we're so used to writing V of x, but in this case, because again, we're dealing with a function in terms of t, that would be V of t. So determining my integrating factor, the integral of R over L dt is R over L with respect to the variable t. So in this case, V of t is e to the R over L times t. So once we have that, we take our first order linear differential equation. In this case, like I said, it is I in terms of t instead of y in terms of x. But we're going to take it and multiply by our integrating factor. So this equation is going to be multiplied by e to the R over L t. And we start to notice patterns as we run through these problems, but I'm going to write this out instead of shortcutting it. So I have e to the R over L t di dt plus e to the R over L t times R over L I equals e to the R over L t times V over L. And on the left side of this, this is the reverse of our product rule. So what we end up with is this is just e to the r over L t times I. So that is the derivative with respect to t of that is equal to e to the r over L t v over L. And then we integrate that. So integrating both sides gives us e to the r over L t times I equals the integral of e to the r over L times t times v over L. And so before I copy this over to my next page, I really just want you guys to be clear. R and L, that just represents some rational number, right? V over L is representing a rational number. Those are all constants, and so we'll treat them like they're constants when we're integrating. All right, so what I'm going to do now is skip to the next page. And so I've rewritten this, and the goal here, what we're doing, is we're trying to determine a function I in terms of t. So we're going to need to integrate this, and then our last step will be to divide by this e here so that we isolate I. I'm going to leave the left side of the equation off until we get down a little further, just to save me some space while we are working through the problem. Okay, so this is equal to, and keep in mind this is still all over here, it's just carrying down. So v over L is a constant, and we can pull the constant in front of the integral. So I'm integrating e to the r over L times t dt. And, you know, if we were integrating e to the 3x, well, integrating e to the 3x would give us e to the 3x over 3. So in this case, we're treating that r over L, like the 3. And so this integral of this piece, e to the r over L times t, it's still going to be e to the r over L times t, but we're going to divide by that coefficient r over L. And dividing by that coefficient is going to be the same as multiplying by the reciprocal because it's rational. So what I end up with here is v over L. I have L over R, e to the r over L plus c. So v over L is a constant. I'm going to distribute. And I don't have to distribute it to the c because multiplying an arbitrary constant by another constant is just an arbitrary constant. If it was a variable, however, we would need to do that. So for the first part, the L's are going to cancel. We're going to end up with v over R. So I have v over R, e to the r over L t. Oops, I'm noticing I left a little t off on my work up above. Plus c. So keeping in mind what I have up above, that this is all equal to e to the r over L t times I on the left side of my equation, I can divide by that on both sides. And in this case, because I'm dividing by a variable, I'm going to need to make sure I apply that to my c. Okay, so I divide everything that cancels on the left, and now I have I equals v over R. Those guys are going to cancel. The e's cancel in that term. And then we've got plus c over e to the r over L t. So this represents our general solution, but we can find a particular solution because we know the initial value, and what we know is that I equals 0 when t equals 0. Because we said at the beginning of the problem that the circuit was closed at time t equals 0. So cleaning up my problem here, I've got I equals V over R plus C times E to the negative R over L t. And I'll use my initial values. I'll plug that 0 in for I and the 0 in for t. And doing that, 0 there turns that into 1, 0 here. I now have 0 equals V over R plus C, which gives us that C equals negative V over R. So my initial value problem solution, my particular solution, is that I equals V over R plus V over R E to the negative R over L T. And so if we consider what we're looking at here, this represents I in terms of T. So this equation is modeling how the current changes in regard to time. All right, and so to continue our thought process, let's skip to the next page. If we acknowledge that both my R and L value are positive, and we have negative R over L, so a positive over positive would remain positive, negating it, negative R over L is a negative value. So then, if we think about E to the negative R over L T, so as T becomes infinitely large, this term goes to 0. So this zeroes out. So if we look now at the limit of I as t approaches infinity, that would be doing the limit of this function. V over R minus V over R e to the negative R over L t. So as we just said, this is going to zero out, which means this is going to zero out. And essentially, we're just taking the limit of a constant. And the limit of a constant is the constant. So the limit as t goes to infinity of I is essentially just going to equal V over R. And what we can say is that any given time, the current is going to be theoretically less than V over R, that value. But as time passes, that current starts to approach a steady state value. It approaches it but never reaches it. And that steady state value is this V over R that we're looking at here. And I'm going to pull a picture in from our text and that kind of explains it a little better. And so I've grabbed that picture for us, and what we can see is that if we were to graph the solution to our differential equation, this function I in terms of t, as t becomes infinitely large as we go this way forever, my graph approaches that asymptote at my steady state value, where the current is the ratio of voltage divided by the resistance.